So let's now consider something that's more challenging. So here's my new question. So instead of thinking of something that has like two delta functions in it, what if I have instead, what if v of x is a double bump, a double square bump? So my potential now is going to appear as follows. This is v of x, and it's going to have, along the x-axis, it's going to have the original bump potential that I had with the same height as before. So in this region, here's region 1, this region 2 will have the same K2 that we had when we had just the original square potential over here, which of course then has its own width here, A. And then what I'm going to do is after some distance, and we're back to a type 1 region, after some distance, which might be different, so I will call this distance here L, I'm going to have a second identical bump with the same exact height as the first bump. So again, this is a type 2 region. Before I get out into the type 1 region, it will have the same width A that the original bump had, like so, and then it goes back to 0, and this now is going to be my scattering potential. Now, let's consider what it would take, for example, to calculate the transmission coefficient for this system. Now, this system is definitely more complex because now I have 4 different places where I can scatter, either transmit or reflect as a fundamental process. We'll begin by considering the transmission coefficient. Those seem to be a little bit more straightforward to calculate, and we'll begin with the simplest possible transmission process, which would be if I just sail directly all the way through. Now, we can figure out, I think, what the coefficients for this term are going to be. As I come across, my first fundamental process then is T plus, where I'm transmitting across an up step. Then I have to propagate across. This is the same P that I had up above because it's wave vector 2 across the same distance. Next, I have to transmit across this downward step, so there's going to be a T minus at that location. Now I propagate across a different distance with a different wave vector. So there's going to be a different P, which I will call P prime. Then here I have now yet another process where I'm transmitting across an upward step. That's a T plus. This P is the usual P that goes inside of my bumps. And then finally I transmit out the other side. This will be a T minus. Where then all of these quantities are exactly as they have been defined before, except that now also we have a P prime, which we're going to define then, and the definition of P prime is going to be, again, it's an exponential, e to the I, you use the relevant wave vector, in this case it's wave vector 1, so that's e to the I k1, and then you multiply by the relevant distance that you're propagating, L, like so. And this then would be the first term in order to determine the transmission through this now double hump system. Now here we begin to see where this is going to become a much more complicated problem, right? Because there's all kinds of processes that I have to consider. It's not as clear as in the previous case where there's just one kind of ricochet. So, for example, right, I could have a path where I propagate in here, and then I might ricochet a few times, and then propagate across, and then maybe ricochet some more times. And I actually don't have to just ricochet back and forth on this side an equal number of times to this side. And I could also ricochet from this front end to one of the intermediate locations. Or I could just ricochet in between these two. And in fact, if you think about this carefully, you will realize that although in the previous case where we had an infinite sum, at least the sum was equinumerous with the integers, right? It was in each term, there's one term here for every single integer, right? Now, which would mean we have a countably infinite number of sums. terms in our sum. Now, though, if you think this through carefully, we actually have an uncountably infinite number of terms in the sum that we have to calculate. It is far, far more complicated to calculate all of the possible terms and reflections here than anything that we've seen before. So we need some kind of organizing principle, some way that we can simplify our calculation to make it much more manageable. I'd like you to, spend a little time thinking about what that might be. You can pause the video, actually, if you would like, to try to think about that. What could we possibly do? So here's the basic idea, right? One thing we could do, for example, is to realize, well, I'm pretty much just scattering between these two step potentials as a unit, right? It's still basically, like with the delta function case, a scattering back and forth between two objects, except now the scattering amplitudes that I have are not just some primitive amplitude, but they are literally just the capital T and the capital R, which we've already calculated for the single bump. So I can just treat this portion here as a single unit whose net transmission and reflection coefficients are a T and an R. And likewise for this number 2, I can treat it that way as a T and an R. Now, we can actually begin to see why this is actually a reasonable approach, why this is possible. It really is just a way of kind of organizing the various terms that we can have. So let's take a look at this complicated process that I had indicated here. Right? This is just one of many possible processes that have the following feature. That feature is that I come into this first region, right, and I may ricochet some arbitrary number of times here. I'll just make this wiggle back and forth to kind of indicate an arbitrary number of times, and the number of ricochets that I will have here I will call n. And n could be, of course, 0, 1, 2, etc. ricochets, right, that I'm going to have here. Then when I'm done ricocheting through here, I can propagate across, and then I enter into the next region is one possibility for me, and I could ricochet in here some other number of times before I finally come out the other side. So this is going to be m, which could have been 0, 1, 2, 3 ricochets. Now when I do this, notice that the case I had drawn up here was a special case. There were 2 ricochets and 2 ricochets. So this was the n equals, what I had drawn was the n equals 2, m equals 2 case of this more specific case where I have an arbitrary number of ricochets. Now, of course, there are even more complicated diagrams that could happen because I could come in, have an arbitrary number of ricochets, transmit across here, ricochet over here an arbitrary number of times, but end up then reflecting back across this barrier, then undergoing more ricochets until I finally transmit over to the right, where then finally I could have more ricochets before I finally transmit.